Hello guys, good evening. Can you hear me?
Yes, sir.
Okay. Just 2 minutes. Let's others also join. Who is this Heisenberg? Okay, guys, one small request. All of you, please use your name, to log in into this meeting. Okay. You can rename yourself. So all of you, please, your first name, if you put, that would be better. Who's this Smithil? Please write your first name. Fine. Okay. So where were we last class? What have we done? I think we were doing elimination, right?
Yes, sir.
E1, E2 elimination. E2 elimination we have done. I think we have also done the stereochemistry of E2 elimination reaction, right?
Yes, sir. That's enough.
Yes, sir.
Okay, fine. So let's next we'll start with, sometimes what happens, we'll continue with this stereochemistry only. Next time what happens, oh, just let me share the screen first. I forgot. Okay. Yeah, it's visible. So you know what, sometimes what happens, they'll give questions in Fischer or Newman projection. Okay, means E2 reactions when the questions are given in Fischer or Sawhorst or Newman projection. Okay, in that case what we have to do, right? Okay, so write down, if the question is given in Fischer, Sawhorst or Newman projection. Okay, so we are going to discuss or understand the stereochemistry when the questions given in Fischer, Sawhorst or Newman. Newman means eclipsed form if it is given. So second, Newman. Okay, eclipsed form of this. So what we have to do into this, we have to convert all these into eclipsed staggered form. Okay, you have to write down the staggered form. Okay, so now you see how to do this kind of question. Suppose the first one is, we have this molecule. CH3 H D. Here we have CH3 and H. Here we have Cl. Okay, and we are heating this with alcoholic KOH. And what is the product we get? Okay, so obviously when you look at the molecule, it is what? It is alkyl halide only. Yes or no?
Yes, sir.
It is alkyl halide. So obviously with aqueous KOH, alcoholic KOH, what happens? Removal of HCl, elimination reaction. Okay, so what is the product we get here? Obviously we'll get an alkene, but what kind of alkene? Cis or trans? That's the question. Okay, so what we do in this kind of question, we convert, first of all, it is eclipsed Newman, right? This molecule is eclipsed Newman. So we convert this eclipsed Newman into staggered eclipsed. Staggered eclipse. Okay, what's your name? It's, who is this? Heisenberg? Just a second, guys. Who is this Heisenberg? Please use your own name, original name. Otherwise, I have to remove you. Okay. So so eclipse Newman, we have to convert this into staggered Newman. For that, what we have to do? We have to rotate one of the carbon atom. We know this is the front carbon and this is the rear carbon. Okay, so see what we do, we'll rotate one of the carbon atom or both carbon atom in such a way so that the chlorine and hydrogen on the other carbon should be at anti-position to each other. You see, this chlorine, if you look at this structure, this chlorine is present at the rear carbon and this hydrogen is present at the front carbon. Okay, so we'll rotate the molecule in such a way so that this hydrogen and this chlorine are present on anti-position to each other. Okay, so you see what we do, this one, the rear carbon will rotate in this direction, that is clockwise, and we get this. So when you rotate, you'll get this structure. We'll get chlorine here, CH3 here, and H here. And front carbon, if you rotate, you will get this structure in which the hydrogen is present on the top, chlorine is present here, D is this side, and CS3 is this side. Did you understand this? This is what we do. Means the front
sir,
carbon.
I didn't understand what you did.
Yes. So what I did, the front carbon, which is this dot, I rotate by 120 degree. So this CH3 comes over here, this H comes over here, and this D comes over here, right? We'll get this.
Oh,
So
okay.
the front carbon 120 degree and the rear carbon by 60 degree clockwise.
Okay.
So you have to rotate this in such a way so that the chlorine and hydrogen on the other carbon, not on the same carbon. This hydrogen and this chlorine are on the same carbon. This hydrogen on the front carbon, this chlorine on the rear carbon. So we have to rotate this molecule in such a way so that the chlorine and the hydrogen atom on the other carbon should be at anti-position from each other. So this structure is staggered. This is eclipse staggered, if you know. We have discussed this in isomerism, right? Staggered form, eclipse form.
This is in the middle of the reaction, right?
To write down the product in this.
Product,
It is not the mechanism. I'm not discussing the mechanism. I'm just discussing you how to write down, because you know this is alkyl halide with alcoholic KOH. Obviously, it goes under E2 elimination, right? So product will be an alkene. Yes or no? So how to write down the structure of alkene? So for that, you have to convert this into staggered form. If Fischer is given, again you have to convert into staggered form.
So, sir, you have to convert it to staggered and then continue the reaction.
Yes. No. See. Okay. You don't. When you get this question, you don't have to write down this structure here. This is just for your understanding. Means how to write down the product. The overall reaction is what? Alkyl halide with this gives you an alkene.
Gives you an alkene.
But what should be this alkene? It is cis or trans. That you should understand, right?
Okay.
To understand this, whether it is cis or trans, you have to do this. Okay,
fine.
Now, next step, what you have to do, this hydrogen and this chlorine, which are at antiposition, this two comes out on reaction with alcoholic KOH, and you get a double bond between this front carbon and the rear carbon. Now, you look at this structure, both CS3 are on the same side, H and D are on the same side. Then what should be the structure here? The structure would be this. Same side, H and D, same side. So this is cis alkene. Understood this? Yes or no?
So the point of rotating is to get them in anti-positions, right?
Yes, because the elimination, E2 elimination, always takes place from the anti-position. Means first Cl minus goes out, and from the anti-position, H plus comes out. You look at the previous class, the last thing that we have discussed is stereochemistry of E2. Just before this, what we have discussed, you see that I have discussed over there that hydrogen comes out from the anti-position.
So it should be a D over there.
Yes or no?
Yes, sir.
Correct. That's why we have to do this. We have to take this hydrogen and this Cl at anti-position from each other.
And then you just eliminate them, right?
Yes. Just eliminate HCl, you'll get a double bond.
Fine.
So it should be a D over there also. It should be a D attached to the carbon right there.
Yes, here we have this. Sorry, by mistake. This is D. Clear? Got it?
Yes, sir.
Now you look at this one and write down the a formula of the product into this. Suppose we have CH3 here and H and D, right? And here we have CH3. This is Cl and this is pH with alcoholic KOH, and we are hitting. Done. So here what
Yes,
we do,
sir.
we get cis or trans?
Trans.
Trans we are getting. So what we have to do? We are just trying to understand the product here, because mechanism we know. Mechanism is E2, we have discussed that. So this rear carbon will rotate by 120, clockwise 120. This CS3 comes over here, this Cl comes over here, and this 120 or what?
So rear will rotate 60.
80.
This will rotate 60, and this
Front will rotate
the front one will rotate anti-clockwise 60 degree. Yes or no?
Anti-clockwise by 120, sir.
120. Yeah, correct. So front anti-clockwise 120 and rear clockwise 60. Correct.
Yes, sir.
Yes,
So this is somewhere this position will have. So this rotation is 60 degree. This is also 60 degree, and this is also 60 degree. And the front one will rotate 120 degree. This chlorine will come over here, and this H will go over here, right? But that is not the point. The point is we have to understand whether this CS3 and CS3 are overlapping or not. It is not, because this CS3 will be here and this CS3 will be here, right? Okay, so when you draw the structure here, the structure you will get something like this. So I'm directly writing it down. We get C double bond C. Both CS3 will be on the opposite side. And one side we have PH and another side we have D. Is it right? So this molecule is trans.
Yes, sir.
So,
Trans. So that is what the question is all about.
so I have a doubt.
Yes.
So I wrote the answer as trans 2-phenyl ethane, but that D, how do you name it?
We don't name that. It's
We
an
just leave it.
isotope, right? It's an isotope. So we don't take this into the consideration. Okay.
Okay.
And it is not ethane. It is
Bu-
something else. 1,
butane.
2, 3,
Butane.
4 carbon we have.
Butene.
It'll be butene.
Butene, 2-phenyl,
Trans.
2-butene.
2-phenyl butene.
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 Butene. Yeah.
Like that. Okay. So isotope we do not consider. Okay.
Okay, sir.
Fine. So this is all these you see Newman to Sawhorse, and then Sawhorse to this structure will get. Okay. Newman to staggered, and then this structure will get. The point is, if you convert this into staggered, you will, understand what should be the possible product, cis or trans will get. Okay. Sometimes the question you will get in Sawhorse projection. Sawhorse projection is this. We have PH here, CS3, parallel, these bonds are parallel. Then here we have PH, and here we have H. On the top we have CH3, and on the top we have chlorine, like this. Same reaction, this with alcoholic KOH, and you are hitting. Okay. So this, first of all, you have to convert into Newman projection. Okay. So how to convert this into Newman? Suppose I am taking this one as the front. Anyone you can take as a front carbon for this. Suppose this one I am taking as a front carbon. So what we get, this front carbon will get a structure like this. This is a front carbon. And this front carbon, on the top, we have CH3. So we have CH3 here. Right side, we have PH. This side, we have PH. And left side, we have hydrogen. So this method, like how to write down this, you should understand. Front carbon, anyone you can take. On top, we have CH3. So CH3. Right side, we have PH. PH. Left side, H. So H. Now, you see, opposite to CS3, what we have? Cl, correct?
Cl.
So this is Cl. Opposite to pH, what we have? CS3. So here we have CH3. Opposite to H, what we have? pH. So this is pH. No doubt. Right. But this is what? This is Newman.
Eclipse.
Yes. It is eclipsed Newman.
So you get trans again.
Okay. Eclipsed Newman. Now what you have to do again into this one? You have to convert this into staggered. Right. So I'm not going to rotate the structure. Just you try to imagine this. How do we get staggered? We'll rotate the rear carbon by 60-degree clockwise. This Cl comes over here, right? This CS3 comes over here. You see this CS3 and this CS3 are opposite to each other, right? pH and pH are opposite to each other. Chlorine and hydrogen are opposite to each other. So when you heat this with alcoholic KOH, then you will get the structure or the final product of this is C double bond C. Both CS3 are opposite to each other and both pH are opposite. Is it clear? Yes or no? Did you understand this? Easy?
Yes, sir.
Easy?
Yes, sir.
So we have seen Newman, eclipsed. What product we get? We have seen Sauer's. Last one we have, and that is Fischer. Okay, how to deal with Fischer projection. So Fischer, again Fischer to Newman is staggered, you have to convert, and then again you have to get.
So could you go back to the previous slide for just 1 second? Yes, sir, done.
Okay.
Yes, sir.
So Newman, suppose we have this molecule. We have chlorine, CS3, H, this is CH3, and this is pH. Alcoholic KOH, and product we have to understand. Could you tell me the product in this? Again, you see, first of all, you tell me it is erythro or trio? Is it erythro or trio?
So erythro.
Erythro, right? So this molecule is erythro. And we know cat and Te, right? Te means trans addition gives erythro, right? So if you have erythro compound, so erythro elimination gives trans. Opposite we have to go. Trans addition is erythro, cis addition is trio. So erythro elimination is trans, right? Trio elimination is cis. Okay. So here the product we get here is this C double bond C, both CS3 opposite side, and one pH will be this side, H will be this side. So this erythro gives trans on elimination. This is like you can understand and you can keep this in mind. Identical group this side and ClCH3 we have here, so it is erythro compound. Now what you can do, you can also convert this into Newman projection, the method that we are using. But this you have to memorize because we already know cis and trans addition gives you trio and erythro, right? So reverse of that also it is true, right? So erythro elimination gives trans compound. So we heat this and E2 elimination. But the method is what? First of all, we'll write down the Newman position of this. Any carbon, we can take it as a front carbon. Suppose this one is the front carbon, I'm assuming. So the Newman is this, the front carbon, and we have CH3 on the top. Right side we have Cl, left side we have H, so we have H here. Opposite to CH3 we have pH. Opposite to Cl, what we have? Opposite to Cl we have CH3, so here we have CH3. Opposite to H we have H, so it is this. Now what we do? Tell me. We'll rotate the front carbon anti-clockwise 60 degree. Fine. Front carbon anti-clockwise 60 degree, right? So this CH3 will come over here. This one, you see. In order to get this chlorine and halogen atom and hydrogen on the opposite side to each other. So here we have chlorine, here we have CH3, and here we have hydrogen. This chlorine and this hydrogen goes out and we get this structure. Yes or no?
So the method of converting those two is just to, like, whatever is parallel in one is parallel in the other.
Yes.
Okay.
That we consider opposite to each other. Not opposite, you can say they are parallel, not anti-parallel, on the same side of the carbon atom.
Okay.
Did you understand this? So all these positions you see, whether you have Newman eclipsed, whether you have Sauert's, whether you have Fischer, okay? In all these, you have to draw first eclipsed, staggered, and then from the opposite side, anti-position, halogen atom and hydrogen you have to remove in order to make a double bond between the front and the rear carbon. Understood? No doubt? Okay. Now the second type of reaction, you see, this reaction was dehydrohalogenation reaction, removal of HX. Now the second type of reaction we have, and we call it as dehalogenation. Dehalogenation. This is what? Dehalogenation reaction, it is the anti-elimination of halogen atom X2. Okay, anti-elimination of halogen atom X2. So the reaction is, see this CH2 X, and this is allowed to react with NaI acetone, or we can also use zinc dust for this reaction.
So zinc what?
Zinc dust, zinc
Okay.
metal we use in this powder form.
So what's written next to NaI?
NaI acetone. Here it is alpha beta elimination, we can say. Both position involves in elimination, so it is alpha beta elimination reaction. 1,2 elimination reaction, that also we say. Okay. Now, first of all, the product that we get here in this reaction is an alkene with the removal of halogen molecule X2. Okay. One more example you see. Suppose we have CH3CH, CHCS3, NaI acetone. Elimination takes place and it gives this. And X2 goes out. Okay.
So here, how do you know what is formed cis or trans?
It is anti-elimination reaction. So opposite side, the elimination takes place. It depends upon what structure is given here. It is not three-dimensional structure. So here you cannot say. It depends upon the position of this CH3 and this Cl. Right. So one of the major product here, like the major product here will be trans, more stable product. Okay. But when the three-dimensional structure is given, we can have the better idea over here. Okay. But it is anti-elimination. So if this Cl goes out from this side, then this goes out from the opposite side. Hence the chances to get the major product here is trans. Like that is the more probability of the product is to get the trans product into this. But when three-dimensional structure is given, then we can talk about it easily. Okay.
So when we have a bisphenol dihalide, the NaI acetone doesn't show SN2, right? So
NaI
acetone? Get the Finkelstein also, the halogen exchange.
That is not only one factor, no. It can show SN2 also. I'll show you some examples. Okay. But that depends upon the degree of this thing, substrate. That depends upon temperature, what temperature we are using. Higher temperature favors elimination reaction. That's what I'm telling you, that all these reactions are very competitive. Here we are talking about the elimination reaction, E2 elimination reaction. Means the temperature will be slightly higher here. So it favors E2 elimination. But yes, like you said, SN2 also possible with NaI acetone. What is that reaction? I'll show you that. Give me just 2 minutes time. Okay. Now you see what happens here. NaI acetone, right? It forms in this reaction. It forms interhalogen compound also. I have written here X2, but that is not correct. I have written this by mistake. This is not correct actually. The correct, the molecule here we get is one is IX and another one is NaX. IX and NaX. So IX is the interhalogen compound. Not that important, just we are discussing it. Okay. So you see here, how does this reaction goes? NaI acetone, it gives I minus, right? This I minus takes this Cl and this bond comes over here and this comes out as Cl minus, which is taken up by Na plus. So Na plus and Cl minus easily in acetone, NaCl can dissolve. Hence this Cl minus and Na plus forms NaCl into this and the reaction proceeds. Right? When you take zinc dust here, zinc is a metal, right? So this metal, the purpose to use metal in any reaction is to provide free electrons. And the reaction of alkyl halide in presence of metal is the carbon halogen bond in presence of free electron becomes weak. And hence X minus goes out by formation of a radical over there. Understood? So Zn dust we use here, the purpose of metal is to use that it provides free electron which weakens the carbon halogen bond over there.
So won't it form Zn(X2)?
It forms finally because when X plus X minus 2 goes out. But the mechanism is what? Mechanism is here will have a free radical intermediate. This X, one electron it takes, one electron comes over here, and this one electron is taken up by one electron of this zinc, because this Zn converts into Zn plus 2 electron. So one electron is taken up by this, one electron is taken up by this. These two radical combines forms an alkene here, and ZnCl2 forms, right? So a little bit different mechanism we have here, but we can use both acetone and Zn dust for this purpose. Only one thing you have to keep in mind: metal gives free electron, which weakens the carbon halogen bond always. Okay. Now, but all these things are not very important. You just know how to write down the product in this reaction. So you see here, if you have this kind of compound,
So if you put a metal there like zinc dust, it would then proceed via the E1 mechanism instead of E2.
that depends. No, see, that depends on, see, that's again the same thing. Only one factor you cannot consider. If the alkyl halide, the substrate is 3 degree, then E1 will be favorable there. We'll do the comparative study of all these four: SN1, SN2, E1, E2. Any mechanism we cannot neglect, right? But mostly here you see this example, I'm writing it down with NaI acetone. In NaI acetone, this reaction favors E2 mechanism here. Depending upon temperature and other things, substrate, leaving group, all these things, depending upon that, the mechanism is E2. But if you take this example, I'll show you this example again. If you take this example where the halogen atom are not present at adjacent carbon, we have chlorine here, CH2, CH, double bond CHCl, right? This with NaI acetone. This proceeds with SN2 mechanism, and the product here is which one? We have chlorine here, chlorine here. So one of the chlorine atom goes out and it gives CH2I, CH2 single bond, CH double bond, CHCl. So this mechanism is SN2, right? The attack of this nucleophile is easier onto this carbon atom, right? 2 hydrogen we have here. That's why Cl minus goes out as a leaving group here, right?
So could you repeat?
Just a second. Here what I said, the halogen atom are not present at the adjacent carbon. No.
Okay.
It is not elimination.
Oh,
but
yeah.
It is substitution here.
Fine.
When halogen atom are present at adjacent carbon, then it involves elimination reaction.
Fine. Cl go out as a leaving group.
Yes. So here it is SN2.
Fine.
Now when you look at this example, we have chlorine here, H, here we have CH3, CH3 with NaI acetone. This reaction involves, we are heating it, this reaction involves E2. And this one is 3O.
We'll get cisalkane. Say cisalkene.
Yeah, this one is 3O. So this converts into cis. So C double bond C, CH3, CH3, H and H.
Sir, does the configuration of the cis matter? Like, can both the CH3s also be on this side and the H's be on the other side?
Configuration doesn't?
Like
You're talking about.
No. Like for cis only, it doesn't matter if the both the CH3s are on the other side, right?
On the left and both H on the right.
Yeah.
Yeah, it doesn't matter. Same thing. Okay. So these two examples you must remember. adjacent carbon halogen atom is there, then it is elimination. Otherwise, the same reaction, same reagent, everything is same. The only thing is position of halogen atom is different. Then the reaction goes with SN2 mechanism. Okay. We can also use zinc dust for this purpose. Okay. One very important example we have discussed about vicinal dihalides. Okay. What happens with Zem dihalides? And here
Alkynes.
here we get unexpected product. Okay, if you do not know this, you will not get it in the exam. You will get it wrong, basically. For example, you see, if you
So
have
could
this
you,
molecule, yes.
after explaining this concept, could you go back once?
I'll go back now only.
Done, sir. Yeah.
Now, when you have Zem dihalides, okay, this on reaction with zinc dust, this gives you this is the reaction we have. How this reaction proceeds, you see. The mechanism, first step is, like I said, metal gives free electron, which weakens the carbon halogen bond, and it proceeds with free radical. Okay. So first step, this zinc converts into Zn plus 2 electron. If you remember, what was that Wurtz reaction? Wurtz reaction follows free radical mechanism, yes or no?
Yes, sir.
And what is the reagent we use?
Sodium plus dry.
Na ether. What is Na there? Is a metal. Metal gives free electron again there. And the mechanism was what? Mechanism involves free radical. So wherever we have metal, especially carbon halogen bond, metals, the reaction, it involves free radical as an intermediate. Okay. So we take two molecules of this substrate here, which is CH2 and Cl2. Okay. So with these two electrons, which is coming out from the metal, one of the carbon halogen bond breaks, and we end up getting this product, a radical here, one chlorine we have here, plus Cl minus, this we get. Basically what happens here, homolysis takes place. So one electron on this one electron on this chlorine, and one electron from this electron, this chlorine takes up and forms Cl minus. Okay, two molecules of this we have, so 2 electron is required. Okay, now this 2 molecule we have, which in the next step, this 2 molecule combines and we end up getting vicinal dihalides, right? CH2, CH2, Cl, free radical combines and we get vicinal dihalide, which again, when we use Zn dust here, because that is present in excess, so this converts into, so basically what happens, Zem converts into vicinal, and then vicinal converts into an alkene. Clear?
So 1 second, can you just keep the screen?
What?
So 1 second, I disconnected. Could you just like not change this thing? Yeah.
Okay, okay.
Thank you, sir. Done.
Correct. So you see Zem dihalides converts into vicinal and then we get an alkene. You see this product is very unusual product. If you do not know this reaction, you cannot even think about this product. Okay, that's why it is important, Zem dihalide reaction. Okay, now could you write down the, I want you to write down the product in this one. If you want, you can draw the mechanism. Two cyclohexane rings attached by a double bond. Very good, Ruchir. So the product is this.
That's what even I got.
Yes. So the simple one, you just need to keep this in mind. Okay, important reaction for exams like JEE, NEET, any exams you write. These reactions are important. So you should know this. Fine. So now we have discussed the reaction of reaction like SN1, SN2, E1, E2. Examples also we have seen, and the other aspects, stereochemistry and all those things we have discussed. And so far we must have this idea that all these four reactions are competitive reaction. Slight change in the condition of reaction will change the mechanism of reaction, right? So I have done a comparison on all these four reactions, right? It is given in different books, okay? And I have made a table here, which I can show you, and I request all of you to copy this down. This gives you an idea of how this comparison goes, right? So you see, can you see this screen?
Yes, sir.
Okay, so this is the comparison we have. SN1, SN2, E1, E2. The halides are 1 degree. It is 1 degree like this. It is 2 degree. It is this. Okay. So if you go left to right, you see SN2 decreases. Any doubt in this? You can copy it down a little bit like after some time. Just tell me, let me discuss all these. Then you can copy it down. The first thing that I have written here, you see left to right we are going. SN2 decreases. It is fine. Because we know 3 degree alkyl halide has tendency to go under what? SN1 reaction. SN1. Hence you see left to right, SN1 increases as well as E1 also increases. Right? Then we can talk about SN1 between SN1 and E1. Depending upon the condition of temperature, which one is favorable. But yes, left to right, SN1 increases, E1 increases. Left to right, if you go, tendency for the substrate to go on the E2 reaction also increases, because elimination gives you more substituted product, hence more stable alkene forms, right? So slight difference we have here. SN2 decreases but E2 increases. Now here you see substrate, I have written the same thing we have here. It is pH CH2X, RCH2 CH2X, 1 degree, 2 degree and 3 degree. Okay. So 5 different substrate I have taken. One is methyl halide, other one is benzyl halide, another one is 1 degree, 2 degree and 3 degree. So bases you see here, we have 3 different types of bases: weak, moderate and strong. Okay, weak bases are neutral molecules, polar protic. Moderate bases are this, okay, I minus, Cn minus, Br minus, aqueous, KOH, etc. Strong bases are alcoholic KOH, NaNH2 and this tertiary butoxide ion. Okay, CH3X, SN2, SN2, SN2. Why? Because it is 1 degree, right? So 1 degree alkyl halide goes under SN2 reaction. That is it. Okay. PHCH2X, it gives you the stable carbocation. So weak base gives you SN1, moderate gives you SN2, strong gives you SN2. Right? Because we know for SN1 we requires what? We requires weak bases. 1 degree alkyl halide, weak base gives you SN2, moderate gives you SN2, strong gives you E2, but the temperature should be high, then only E2 possible. 2 degree, low temperature gives SN1, high temperature gives E1, moderate gives SN2, strong gives E2.
So what if the temperature isn't high?
Which one?
Third
one.
Where you've written E2, sir. If the temperature isn't high, then it's just SN2, right?
Yes, correct. Similarly, we have the last one. So overall, if you compare this, SN reaction favors at low temperature. If high temperature is there, then either we can have E1 or E2 depending upon the base and the substrate. If the substrate is 2nd degree, high temperature gives you E1, right? High temperature, weak base gives you E1. Low temperature, comparatively low temperature, but if the base is strong, then E2. Like this we have. Once you finish, just let me know.
Sir, could you send a photo of this on the group?
I'll share.
Thanks.
Anyway, this slide I'm going to share, no? So you can copy it from there also. Fine, understood.
So benzyl halides will never undergo elimination reaction, sir?
No, it's not possible. You draw the structure, you will understand. Because the benzene does not have hydrogen with it.
Oh, okay, fine, yeah.
Right.
Yeah.
So you can keep going.
Okay. Okay.
So 1 second, sir, you haven't completely finished.
Done?
Yes, sir.
Okay. Now you see this one. Based on this, we'll just try to understand some examples here. Suppose we have a substrate 2 degree. So 3-dimensional structure, dash bond it is. And when it is allowed to react with NaNA3, NaN3, the product in this NaI acetone. RCOO minus Na plus NaSH. Compare this as OH, same thing you can say.
So we're only heating for the last two ones?
Yes. Correct, Ruchir. Yes. You try to compare this with the table that I have given you now. Okay, substrate is 2 degree and these are the bases we are using. Done, all of you?
Done, sir.
Okay, so I'm getting, what about the first one, Vikas?
I wasn't really sure about the first one.
Okay, why?
So I know it might dissociate into like Na plus and N3 minus. So I wasn't
So
sure.
what is that? N3 minus is
So I know
N3.
that's why I didn't know.
See, actually this is, you can write as N3 minus, simply it is the base. So I think this base is given in that table. You see that? Is it?
So it's moderate base.
Right. So it is SN2. So if you compare all these bases and the table that I have given you just now, according to that, this goes under SN2. This also goes under SN2. Remember, E2 is there when we have dihalides with NaI acetone. This reaction is what? What is the name of this reaction?
Halogen exchange.
Finkelstein reaction.
Finkelstein.
Yeah, it is Finkelstein reaction. Exchange, halogen exchange reaction. Okay. This is again SN2, NaSH, again SN2. This one is a strong base plus we are heating also. So it is E2 and E2. Got it? So the product here, what is the product we get? Obviously in SN2, what happens?
Warden inversion.
Inversion in configuration, right? So chlorine is coming out of the plane, means the base will go into the plane.
So what's the structure of N3 minus? I thought it didn't
is
exist.
this. N, no, it is. N this thing, N triple bond. So we can draw. Even, we have this thing. We can also draw this way. N double bond, and a lone pair here. Right? We have a, an intermediate. I have discussed that. Nitrines. So nitrines intermediate forms when we have this kind of compounds. Here it is not possible, but we'll discuss this, how this molecule, the structure is, and how it involves the formation of nitrines. Okay, we'll discuss that later in amines chapter. Okay.
Okay, sir.
Right. So here the base is I minus. So again, the same compound with I from the back side, it will attach over here. Here what will get attached? RCO minus. Here it is SH. Here it is OCH3. OCH3 it is? No, because it is elimination. Right, so this gives you what product? ZF. Why ZF? Because small base, right? But here the tertiary butoxide ion, the base is bulky. So Hoffman is the major.
So why can't the second last one undergo E1 mechanism?
How it is E1? We are having this is 2 degree, right? Solvent is what? Solvent is polar protic.
Oh yeah, I forgot about
solvent is polar protic, right? And we are heating it. Right? The carbocation forms is not that stable, 2 degree.
So with 2 degree, we don't have E1?
It depends. See, again, I have given you the factor, no?
Yeah.
All those factors gives you the net mechanism of the reaction. So actually, when I say that this mechanism, or even if in the book, if you study, sorry, the mechanism is SN2 here, it means depending upon the reaction condition, the reaction follows SN2. The net effect is like this only. It goes under SN2, and hence in the book it is given as SN2. Right?
Yes.
So here also you see the CH3O minus, it is strong base. Yes or no?
Yes, sir.
It is a strong base and 2 degree alkyl halide we have. The strong base with 2 degree alkyl halide goes under E2 elimination at higher temperature. Okay. That
I thought it was moderate. It's strong.
No, it's heating. No, you see this.
Okay. Yeah. Yes, sir.
So it's very relative. It's very competitive. All the 3-4 reactions that we have. So I know that from that particular table, it's again difficult for you to identify whether the mechanism is E1, E2, SN1, SN2. But yes, between this elimination and SN1, you can have the idea what reaction is possible. But then whether it is SN1, SN2, you must have some confusion into that. So the best way is to eliminate those kind of confusion is to solve questions. When you solve questions, you will get wrong answers, and then we'll try to understand that what is actually happening here. Right? So practice is very important in this. Okay. One more question you see here. What is the product we get? Tell me. Suppose we have CH3. Write down the major product.
sir.
Alcohol through SN2. What is the mechanism?
E1, sir.
There's an
E1, sir. E1, sir.
Why elimination?
So it's not
The
hot.
high temperature.
80 degrees.
It's the
At 80 degrees Celsius, and you're
high
using.
temperature.
Okay, got it, Ruchir? Ruchir Parekh. Okay,
Yes, so but wasn't the temperature supposed to be higher? We written
that's what
170.
80 degrees Celsius is high temperature, no?
So before we written that high is like 170 and below 140 is low.
No, I think for carbon halogen it is 25 and 50.
Okay, sir.
To below 25 it is SN1, and like 50 above it is E1.
Okay, yes, sir.
Okay, so you can think about two possible mechanism here, SN1 and E1, but again you can eliminate SN1 easily since the temperature is high. 80 degrees Celsius favors elimination reaction. So what we get first of all we'll get a carbocation, positive charge here, then rearrange, we'll get a positive charge here, and then elimination, right? So I'll write down here, the carbocation we get in the first step is this. Then we have methyl shift. In order to get more stable carbocation. And then we have elimination of H+. So this probably gives you one of the product as this CS3, C double bond C, and the another one is we get a double bond here, so it will be C single bond CH CH3 CH3, and we have single bond CH3. This is the two possible product we get, but the major one is what? The more substituted one.
So I had a doubt, sir.
Tell me.
So does high temperature and low temperature vary according to what the bond is?
Obviously.
Okay.
Bond strength, because you see, it's very logical and you can understand. Elimination is nothing but the removal of ions, right? Or dissociation of bond. So higher temperature, if you want to break a strong bond, you require more energy, more temperature. So it depends, yes.
Yes, sir.
Okay, so this is it for E1 and E2. The next reaction we have to discuss is, write down.
Can you show the slide once again? Please?
Yeah, this.
Yes, thanks.
So if this was at a lower temperature, then it would do SN1, right?
Less than 25, it favors SN1. Then substitution takes place, you'll get an alcohol in that case.
Yes.
Okay. Okay, next reaction you see, we have E1 CB. Here this CB stands for, write down, conjugate base. CB stands for the conjugate base. Write down in this. If carbon and the leaving group bond, if carbon and the leaving group bond is stronger than the carbon hydrogen bond, at beta carbon, hence the removal of leaving group is difficult with the base. Removal of leaving group is difficult with the base in comparison to the hydrogen atom at beta carbon. In comparison to the hydrogen atom at beta carbon. Hence, next line. Hence, the base takes out hydrogen from beta carbon, leading to the formation of carbon ion.
So could you repeat the last
statement?
Yeah. Hence, the base takes out hydrogen from beta carbon and leading to the formation of a carbon ion.
Thank you, sir.
Okay. Now this reaction is very important. One application of this is very important. I'll show you what kind of question they frame based on this E1CB mechanism. Okay. So now first of all, you see and try to understand what is E1CB reaction and how it proceeds. The first thing, suppose we have a substrate which is carbon hydrogen bond and leaving group. Okay, so with the base, if this bond is strong, then it is difficult to break this bond, and hence this base easily takes this H+ ion. Fluorine you can attach, yes. There are other leaving group also we can use which bond is comparatively stronger. Okay, or we can say poor leaving group. Okay, that also we can consider. We'll see that example. We'll see fluorine is attached.
You work for OH, right?
Yes, OH. That also we can take. Okay, we'll show you that all those examples will show you. So poor leaving group we can have, or a strong bond, both is possible. So what happens? This base takes this H+ from the beta carbon, alpha and beta carbon, and the product here we get is C double bond C plus H B and L minus. Now when you look at this, it looks like a similar reaction, elimination, E2 kind of reaction. Okay, it looks like very similar.
It's like E1 reaction, right?
E1 reaction it looks like, okay. But here the thing is different from E1 reaction. I'll show you how the reaction goes. The first step here is this base and it takes H plus and it forms C negative charge plus HB. This is the carbon ion we have. So the intermediate of this kind of reaction is carbon ion. Till now, we haven't seen any reaction in which the intermediate is carbon ion. Could you tell me any other reaction in which carbon ion is an intermediate? Have you remember tautomerism?
Base catalyzed tautomerism.
Base catalyzed tautomerism. There also carbon ion is the intermediate. Okay, important that one also. Again, so this carbon ion this comes over here and then the leaving group goes out and we get C double bond C plus L minus. Okay. Now the RDS of the reaction, obviously this is reversible step. The second step is the RDS of the reaction, rate determining step. Okay. It is a slow step, hence the RDS of the reaction. Did you finish it? We'll go to the next page.
10 seconds.
So, but if it's a poor leaving group, then how will it just leave like that?
Because of this lone pair, because of this carbon ion that forms. See,
So because it
again
has
you
lone pair repulsion with this.
No, you see what happens. Usually what happens, if the leaving group is very good, then it goes out in the first step only, no, and forms this carbocation. But since this is strong, right, so we made this leaving group to go out. We are pushing it out by this formation of carbon ion. This lone pair, when it tendency to form a double bond here, in this step, we are pushing this leaving group to go out, since it is a poor leaving group.
Okay.
Correct. That's how the thing is going on. So you see, this is the conjugate, base we have here. H plus will take out from this, forms a conjugate base. Okay. Then conjugate base, this lone pair converts into bond pair, and this makes this leaving group to go out in this reaction. Now, the characteristics or the property of this reaction, write down properties. What is the first one? If I write down the rate expression, what should be the rate expression? Rate constant K into what should we write here?
Concentration of conjugate base.
Conjugate base. Okay, this square bracket means concentration itself to the power 1. Okay, so what this one is? Order is
1.
1. With respect to what? With respect to? Conjugate base, right? See, the order is 1 with respect to conjugate base. Hence, the reaction is E1CB. Got it? 1 with respect to conjugate base. Clear? Third point, rate of the reaction is directly proportional to the stability of carbon ion. And we know how to compare the stability of carbon ion. I hope all of you have won't have any doubt in this. Okay. Mainly, fourth point, write down. Mainly Hoffman alkene is the major product, but not always. Generally, Hoffman product forms, but not always. Do we have rearrangement possible in this?
No. No, sir.
Why? Intermediate is carbanion, and the rearrangement of carbanion is not possible. No rearrangement. Rearrangement is possible for free radical for carbocation, but carbanion rearrangement is not possible. Right? Now,
why is it usually the Hoffman product?
Not like mainly it is. I'll show you some examples. You'll understand. Okay, because of the structure we have, it is Hoffman. But in some cases, it may show Sergev. That is also possible. So it's not the the general rule that we have. Mainly it is Hoffman. We'll do some example. You will get it. Okay. Now, like I said, because of the nature of leaving group, this kind of reaction is taking place. So what all leaving group we have, which shows this kind of reaction, E1CB reaction. So write down only few leaving group shows E1CB. For example, we have fluorine, like you said, carbon fluorine bond. If you have NR3 plus, nitrogen has 3 alkyl group attached with it, and we have like H2O plus, H3O plus. Similarly, we have SR2 plus. It is ether actually. OH also shows this kind of. Okay. Now for this reaction, since we have to extract that H plus from the beta carbon, so base must be strong. So need a strong base. For example, we can take, what we can take? A strong base means any negative charge ion, OH minus. We can take RO minus, NH2 minus, etc. Okay. This reaction is favorable at high temperature. Okay. Now the important thing here, that how do we identify that even CB is possible in this reaction? So first of all, the leaving group should be this. These four, if you keep these four in mind, even the important one is fluorine, NR3 and OH. If you keep these 3-4 things in mind, you can identify the reaction, whether it is even CB or not. Okay, I'll show you one example here.
So why is the rate of the reaction proportional to stability of carbanion? The RDS was the leaving of the leaving group, right?
Stability of carbanion is this.
So, right. But the carbanion is forming in the first step, right?
Right. And this is converting into alkene. Right. If that carbanion is not stable, right? If the carbanion is not stable, then this has less tendency to convert into alkene. Not stable means it will convert into alkene. If it is stable, then the reaction is difficult.
So, but in SN1, we said that like the first reaction was the RDS.
Yeah.
The formation of the carbocation was the RDS in SN1, and there also rate was proportional to stability of carbocation.
So over here, shouldn't it be inversely proportional? Because if you have a very strong,
I think just a second. I think the intermediate is carbonyl. No, carbonyl is the intermediate. I think I made a mistake here. Just a second. This is because if you remember, the formation of intermediate is the slow step. This is the RDS. This would be the fast step we have, because once it forms a double bond and leaving group goes out. So first step is the slow step RDS, and hence stability of carbonyl matters over here. Got it?
So then
Yes,
then the
any
order
reaction you see, I'll tell you one thing. This is very common in all the reactions. In any reaction, formation of intermediate is slow, always. And then intermediates converts into product, that is very fast reaction. If this forms, this formation of this is difficult. But once it forms, it converts into the product easily. So first step is a slow step, RDS. Okay? Change that. I made a mistake there. Okay.
So but the order.
then how is it E1?
What?
How is it still E1? Because now it will depend on concentration of base, right?
Base with we required a strong base, no?
No. So like now the order is 2, right?
No, it's not 2. You see here, it depends upon the concentration of this. See, it's like, I'll tell you one thing. The rate expression that we write, no, this expression, you're talking about this expression, correct? This is experimentally determined. We are not drawing this from the equation that is given. It is experimentally determined. We cannot write down this. And in this reaction, the rate is observed to be directly proportional to the concentration of conjugate base. Okay, we can have this as 2 also. See, this 1 is not because that this stoichiometry coefficient is 1. This is 1, hence the expression there, R is equals to K concentration of conjugates to the power 1. This 1 is not there since this stoichiometric coefficient is 1. Just a second. Yes, guys. So what I was talking about, that this expression is experimentally determined. You don't get confused here that the stoichiometric coefficient is 1, hence we are getting it as 1, right? So this value here, this expression, everything is experimentally determined. It has nothing to do with the reaction that I have written here. Are you getting it? This thing we'll discuss in detail in chemical kinetics. That rate, and that's why we always say that order is the experimentally determined quantity. Okay, it is theoretically we cannot determine. If you say the order of the reaction is 1 or 2 or 0, this number 0, 1 or 2 order is experimentally determined. We cannot do anything into it. Okay, so this rate expression is experimentally determined. Okay, experimentally determined, and we always write down this rate law expression with the slowest step of the reaction.
You hi.
You can join me.
Yes, yeah, correct. Did you get it?
Yes, sir.
Okay, so this rate thing we'll discuss it later in chemical kinetics in detail. How do we get this rate expression? Okay, now coming back to the question here, suppose the question is this: how do we understood, or how do we get this idea that in this particular molecule even CB reaction takes place? Suppose nitrogen has 3 alkyl group here, positive charge, CH3. We have OH minus. What should be the product in this reaction?
So over here, the double bond will be with the first CH3, right?
First CH3.
Won't it just be in the middle? The second from the left is the alpha carbon. So the beta carbon will be 6 hydrogen.
Just a second, guys. Let me just cross check this. We have here.
So do we take Hoffman here or?
Huh.
So do we take Hoffman product here?
Huh. I'll just do this. Wait.
It should be, because if you put it on the other one, then it'll be less stable.
Okay. First of all, you see, this is the leaving group, right? NR3 plus. Yes, this is the leaving group. But you know, carbon hydrogen bond, nitrogen bond is a stronger bond. It's a covalent bond, a stronger bond. So it's very difficult to break this bond. So this base, what it does, this will either take H plus from this carbon or this carbon, which are the beta carbon we have. Okay, so which carbon loses H plus ion here, in which the conjugate base is more stable.
That's the first answer.
If this loses H plus ion, it forms CH2, negative charge, single bond CH, NH3, NR3 positive charge, CH3, CH3. This is the conjugate base we get. Stable conjugate base is this. Now what happens, this conjugate base, lone pair converts into bond pair, and then this leaving group goes out, and we end up getting the molecule which is CH2 double bond, CH, single bond CH, CH3 and CH3. This is the product we get. Understood? So this is Hofmann product we get. Since carbanion forms as an intermediate, that's why Hofmann product generally forms in general. Understood? So how do we get this idea that mechanism is even CV? The first thing, the leaving group should be what? Leaving group should be OH, NR3+, fluorine, etc. Strong carbon and this atom bond we should have. If this bond is strong enough, then this base would easily take H plus from the beta carbon, forms carbanion, and the reaction proceeds. Understood this? Could you write down the product in this reaction? Oh, we are heating this also. We have OH minus. We are heating this. Mechanism, obviously, we have even CB, which is not given in the question. I am writing it down. Even CB. Tell me the final product here. Try this, I'm coming.
Won't it just be a hexene ring, like a normal thing?
Yeah, that's what I was thinking.
Right,
Like,
That's what I got.
yeah, both the beta carbons are the same. Right?
Same, sir.
Yeah.
You guys sure there's not going to be any weird ring?
Yeah, he said try this, so I know something's gonna happen.
Maybe he forgot the benzene ring or something.
But like both the
Maybe
beta
there'll be a
carbons
double
are same.
bond. So because of that, resonance will be.
Where? There is no double bond.
No, I'm telling if that should have been a question. Then
Yeah,
anion
yeah,
will be stabilized.
Correct.
Yeah,
That's what even I thought.
We can form on the side also. The N has that R. The other R
No,
can form ethane.
but that's part of the leaving group, no?
It need not be. No, we can take the cyclohexane as R instead.
Okay, did you get it?
So will it just be a hexene ring?
What?
Will it be a hexene ring?
Hexene.
Yes, sir.
Cyclohexene.
Okay, fine. That is understood. Cyclohexene, all of you are getting. Okay.
I have a feeling there's a
Wait, no, it's not. No, Richard is right. Instead, the cyclohexene.
It'll be ethene.
Yeah.
Ethene. Oh, who got this ethene?
Then Richard got. No, actually, Richard got. I didn't get it.
Okay, could you explain who got ethene?
So we can form it on this side because that's 2 degree and this is 1 degree.
Yes.
We form
Yes.
it for here
Okay,
on the
Richard
matrix.
got ethene. Fine. You see, actually, what happens? We have to form the more stable carbanion. That is the first objective we have. We'll take H plus ion from that carbon atom, which gives more stable carbanion. You see here, this is how many beta carbon we have here? Could you tell me? How many beta carbon?
3.
This nitrogen, this is alpha, This is beta, and these two carbons are equivalent. This is alpha and this is beta, right? Yes.
Yes, sir.
So either you take H plus from this carbon or H plus from this carbon. So this gives you secondary anion. Yes or no?
Yes, sir.
This gives you primary anion. This one is more stable than this. Hence, the carbon ion that we get here is this. Any doubt? Positive charge on this nitrogen. Then what happens? This forms a double bond and this goes out. So what we get next? We get CH2, double bond CH2 plus this is the answer we have here. Easy, good one.
Yes, sir.
This one you try. It's not to understand the stability of carbon ion, you have to apply all those resonate like electronic effects, plus and minus and whatever it is. Okay, you see this example OH here, and then we have OH minus.
Carbon ion will be resonance stabilized with the double bond.
And we have here E1CB. So you see, for the first step is what? The first step is we know this leaving group is not that great. Okay, it's a poor leaving group. Especially the medium is basic. So in basic medium, it's a poor leaving group. Yes or no? Anyone has doubt in this? Acidic medium may protonation is possible and this poor converts into good leaving group. Correct? But the medium is this basic, so it's a poor leaving group. Hence, this reaction goes under what? Even CB mechanism. This base will take H plus from either from this carbon or from this carbon, depending upon the stability of carbon ion. Which carbon ion is more stable?
To the right.
One to the left.
Middle one, right? Middle one. Yeah, the center one. So we'll get a carbon ion here. And next what happens, this comes out and this go away. Sedgef alkene we get. So here you see, we are getting Sedgef alkene. So that's why we say that in general we'll get Hofmann, but in this kind of cases where some electronic effects are there, then Sedgef alkene is possible.
So this was,
Understood,
so this one was due to the resonance of the double bond. Why we got the center carbon as carbon ion.
Resonance of electron withdrawing group of this double bond O.
Yes.
This carbon ion becomes stable.
Okay.
Understood, Pradam, why we say a Hofmann generally and all these?
Yes, sir. Got it.
Correct?
Yes, sir.
One more. Write down the product in one single step.
Done.
Done. Mechanism is E1CB and the product is this double bond will be as it is and we get a double bond here. Correct?
Yes, sir.
Try this one. 2 more we'll discuss.
Sir, is it not possible due to bridgehead position?
Think about it.
So that nitrogen one, does it form ethene again?
Yes, sir. Even I got ethyl. And then the amine, the nitrogen thingy.
Okay. See how many alpha carbon we have here?
2.
2, sir.
Why 2? Do we have 3?
3, no?
1, 2, and 3.
But 2 are equivalent.
So how 3?
1, 2, 3.
So Brandon is the same thing.
These two are same thing, but total we can count 3.
Huh.
You know, alpha carbon, alpha hydrogen we count like that, right? So 1, 2, and 3.
Yeah.
And beta is, this is 1. This is also the same thing, and this is the third one, correct? This beta carbon you see, it gives you tertiary anion. Yes or no?
Yes, sir.
This beta carbon gives you secondary anion, right? Now you see the application of Brett's rule here. Obviously, this OH minus takes H plus from the beta carbon. This beta carbon won't lose H plus because tertiary anion is less stable than the secondary. Understood? So if I write down this one, do you have any objection in this? Negative charge here?
No.
No. Now, this converts into what? This lone pair converts into
Bond
a pi bond, right? A pi bond. So will this lone pair, should this lone pair shift on to this carbon or to this carbon? Which one is right?
Down.
One.
Down.
Down.
Because of
This
resonance with
is not
nitrogen.
possible. Yes.
Oh yeah.
The second thing is this shift is not possible. Why? If this happens, then what happens? You see, the orange one gives you this. Gives you this, correct? And The red one gives, the white one gives you this. Here you see this shift itself is not possible because this forms a pi bond here, right? Like this, it forms a pi bond. Then there is no leaving group attached to this carbon atom, no. So that when it converts into pi, one bond is not breaking. This hydrogen won't go out as H plus here, right? Hence, this shift is not possible. But when this shift over here, to stabilize this nitrogen, this sigma bond goes onto the nitrogen atom like this. And this bond won't be there, we'll get the structure like this. So this is not at all possible actually. You can ignore this.
So what's the leaving group here?
What?
Leaving group?
Yes, tell me.
So the leaving group, what's the leaving group? Is the pink one the final structure?
Yes, this one.
Oh, there's a positive charge. Oh gosh.
We have positive charge on nitrogen, no? So this will take this bond pair of electron. And this side is not possible because there is no leaving group attached to this carbon atom,
Yes,
which could go out when this converts into pi bond. And hence the structure is this. Clear? Right? This one is easy. I'll write down the answer here. What is the answer in this one? pH CH2, right? Where should we have the double bond? Is this correct or this one?
Second one.
Second one.
Because again, this lone pair is what? This negative charge is resonance stabilized. So this is SETJEF, the major product we are getting. This won't form, or minor product will be that. Okay. So this is the reaction we have. We call it as E1CB reaction. The basic reaction is this. Now, based on this, what kind of question they ask in the exam, JEE exam especially, okay, that we are going to discuss based on this reaction. So this reaction that we are going to discuss now, we call it as Hofmann exhaustive
Sir,
yeah.
Could you just go back to the previous slide? There was a network problem.
Just a second. Hofmann exhaustive methylation. It is the same reaction that we have in this E1CB, but how they frame the reaction, frame the question, that we are going to understand.
Thank you, sir.
Okay. So Hofmann exhaustive methylation means methylation first of all takes place. Access methylation takes place. So suppose for this one, I am taking the simplest example here, and the molecule is CH3, CH2, CH2, NH2. It is amine, 1 degree amine. The question is this with CS3I excess gives A, with AgOH heat gives B. So what is B here? Right? So when you look at this molecule, okay, you won't get any idea that what is the mechanism of the reaction and how the reaction proceeds, first of all. Okay, but this is the similar reaction that we were doing, E1CB. How this reaction gives you E1CB mechanism, that is the first thing we should understand here. Now, if I write down here, this CS3 has partial positive charge and partial negative charge. It is fine with you? Okay. So what happens in the first step, you see? In the first step, this substrate CH3, CH2, CH2, NH2, this lone pair of nitrogen attacks on the partial positive charge carbon atom, and I minus goes out as a leaving group here. This converts into CH3, CH2, CH2, NCH3, H, positive charge. Do you have any doubt in this? No?
No, sir.
Correct. Now, next step, what happens to stabilize this positive charge? H plus comes out. So this converts into CH3, CH2, CH2, NCH3, H. Is it fine? So 1 degree amine converts into secondary amine. Okay. Now, could you tell me, since this CH3I is in excess, so this reacts with this molecule again? And if I write down the product directly here, that would be this CH3, CH2, CH2, NCH3, CH3. Do you have any problem in this? I want a response from your side. Tell me, it's important. If you don't get it, after this, the reaction is fine. But if you don't get it, you won't understand this. See what happens, again this lone pair will attack onto this CH3, I minus goes out, same step it is, exactly same steps. We'll get this. 1 degree converts into secondary, so secondary converts into tertiary, right? And then again this tertiary converts into quaternary, which is this. Is this fine? Is this fine? First,
So,
tell me.
why will that?
Understood this?
Why will the last step take place? Isn't that forming a positive charge?
Because still we have lone pair here.
Okay.
No.
Yes.
Ammonia, like amines, forms quaternary salts, quaternary compounds, because it has tendency to lose lone pair in every step. And that is why this product is also forming, because CH3I, we are taking it as excess. If it is not in excess, this is not possible. Clear? You can type CLR, guys, quickly. All of you understood this? Fine. So we'll get this. Now, you see, this is the first product in this reaction, which is A. Now, if you try to compare this reaction, AgOH gives OH minus. This converts into what reaction?
E1CB.
Now it is E1CB, because the same kind of compound we were using earlier, if you remember. If you look at the other examples, we have this only N3 alkyl group positive charge on it. Yes?
Yes, sir.
Yes.
No doubt. Correct? So after this, we have E1CB reaction. So could you write down the product in this? What is the product we get? Beta carbon, so just remove H plus, because this OH minus takes beta carbon, H plus, and we'll get an alkene. Propene, right? Yes.
Yes.
So the product here is
Propene.
CH3, CH double bond CH2 plus what we get? Plus so you see we have started from amines and will end up getting alkenes. They have asked this question many times in JEE exam. Not exactly this, but similar. The concept was this only.
Sir, in alkyl halides, didn't we say AgCN is very covalent and can't break down to give Ag plus and Cn minus? Isn't that same thing here?
No, AgCN, not Cl.
So, but if AgCN is covalent, shouldn't AgOH also be covalent? Because N and O have similar electronegativity.
No, fine, but the property there is the bonding. If you see Ag, you're talking about AgOH.
Yes, sir.
AgOH is what? AgOH is a salt. It gives Ag plus and OH minus. It exists in this form. Strong electrolyte it is. AgCN is what? AgCN, the bonding is like this. Right. Silver carbon bond is stronger here than silver oxygen bond. OH minus is quite stable. Then Cn minus. See, this bond will break, carbon will take chlorine, this bond pair of electron. When this is electronegative, then only it's possible, no? But
Yes,
the electronegativity difference is not that great here. So hence the bond is covalent here and less tendency to dissociate. But this is fine with AgOH. It converts into Ag plus and OH minus.
Okay, got it.
Okay. So that's the thing. Anyways, so this you understood, right? So they won't ask you this question directly. They won't give you this and then ask you to write down the product. They frame the question like this. Start with amines and then they'll give you this question. Okay. So this till here you see it is the methylation of amine. Yes or no? At every step, the methyl group is getting attached to the nitrogen atom. Here, then here, sorry, here, then here, and then here. Correct? So hence the reaction is called as what? Exhaustive methylation. Okay. Now they can ask many different kind of question here. Suppose if you have CH3, CH2, like suppose if I give you this example, just write down the product. CH2 NH2. Okay. And here we have hydrogen, CH3 and CH3. This is a molecule with CH3, CH2I excess gives A. Then we have suppose OH minus heat gives P. What is A and B in this? Okay. Correct, Ruchir. Ruchir Parekh. Okay, so what we are getting here? After this exhaustive methylation, What is A? A is this.
Three ethyls of the nitrogen.
CH3, CH, CH2, N, positive charge, correct?
Yes.
Yes, sir.
This is A, and now with this base OH minus, either this base will take H plus from this carbon, because all these are equivalent. Beta carbon is this and beta carbon is this. So which carbon is more stable? Which anion, where we have more stable anion? This one or this one?
Ethyl.
This anion is more stable.
Yes.
So what we get? We'll get the major product as ethene, which is CH2, double bond CH2, plus other products we'll get here. No doubt in this?
So how do you name the other product?
What is the other product we get?
So you get one a huge group.
This is the product we have now.
Yes, sir. Yeah, that's right.
So it is amine.
Yeah.
Right?
But,
so what is the name of this compound? Methenamine. Easy as Chaitanya. You see this. CH3CH. The same product I'm writing down in this way. Okay?
yeah.
This is methenamine. So this one is N, N diethyl, right? 2-methyl propanamine.
Okay, fine. Yeah, I forgot the N thing. I forgot how to name it.
Right? N, N diethyl, and then we'll write 2-methyl propanamine.
Yes.
Okay. Just a second. So this example, this reaction is very important. Exhaustive methylation. Okay. Okay.
So something that's equally important is getting a break at the right time.
This is Dhruv or Param? Param, right? It's 6. We'll take a break at 6:30. No.
So we shouldn't postpone important things.
Yeah.
So if you
What
have a
is
small topic, we can finish it like in like 5 minutes.
No, I won't start. After this, we have to start intramolecular elimination. So I won't start that and we'll take a break. I just want you to solve 1 or 2 questions and then we'll take a break. Let it be as it is. Okay.
Yes.
Based on this only, just we'll see some more examples 1 and 2, and then we'll take a break. And after break, we'll start intramolecular elimination reaction. Fine. So this is the basic one. So let it be. I want you to solve this one. Double bond we have here, and here we have NH2. Now I'll write down this way. CS3IXS. Let it be, only one will do, and then we'll take a break. Cyclohexadiene. Is it cyclohexadiene we are getting? Okay,
Yes,
fine.
sir.
Yes.
I got
So where the carbocation is more stable, this one or this one?
the down one. I
So the first one.
Resonance table.
Resonance table.
This carbanion is more stable, and hence we get the product, which is this. So it's very easy. It's not that difficult. But only thing is, you should keep this in mind that this is the reaction we have, E1CV reaction. If you know this, you can do these questions easily. That's not a big deal. Okay, fine. So we'll take a break, and after break, we'll start with intramolecular elimination reaction. Okay. We are almost done with elimination. This is the last part of elimination reaction. And after this, we have to see free radical intermediate and its this thing. It's the reaction involves free radical intermediates. Okay. One thing I would like to know, what about your school things? It is going on the school classes or it's over?
Sir, we finished coordination compounds today.
Finished coordination.
Yeah. Yes, sir.
What else you have done in the school?
Haloalkanes and haloarenes.
So haloalkanes, we have done most of the reactions.
Yeah.
Two things are left, we'll do that. But coordination, they have finished.
Yes.
What about other schools?
So we did polymers and the last chapter.
So metallurgy
okay,
and
fine,
polymers.
fine.
That's what
So
we do.
school classes are there now. You do not have school classes because it's holiday.
Yes, sir.
Yes, sir. It ended today.
Okay, fine. Fine. Chalo, theek hai. We'll start it at this is 6:15 now. We'll start it at 6:30. Okay.
Okay, sir.
So could you
Take
leave
a
the
break.
page with the table on it in the braille?
Which one?
So the one which had that table, I couldn't copy the full thing.
Oh yeah, just a second. I'll just show you.
Okay,
You
thank you,
copy
sir.
this. Anyway, I'm going to share this thing with you. Like the notes I'll share after the session. Hello? Yeah, can you hear me?
Yes, sir.
Yes, sir.
Yeah. Okay, so just a second. 1 second, guys. Hello? Yeah. Okay, so yeah, so we have discussed this thing, E1 CV reaction. Yeah. So next reaction you see, write down intramolecular elimination reaction. Okay. Intramolecular elimination. EI. There are 4 different reactions into this, which follows this particular mechanism, intramolecular elimination. Only 4 types we have. The first one is pyrolysis of ester. Now look at this. We are looking at the reaction of esters also. Pyrolysis of ester, pyrolysis of xanthates. This one is not that important. Third one is
What's that word?
xanthates. 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 Pyrolysis of nitroalkanes. This one is important. And the last one is Cope's reaction. You must have heard about Cope elimination reaction. Yes, Cope elimination. This one is also important, Cope elimination. So first type you see, pyrolysis of ester. You see this example? We have CH3, C double bond O, OCH2, CH3. Okay, this is alpha and this is beta carbon. Pyrolysis means cracking. So we generally heat this kind of reaction, just we are heating it. And we end up getting an alkene, which is CH2 double bond CH2 and CH3 C double bond O, OH. Acid plus alkene. This kind of reactions driven by the increase in entropy. Increase in entropy. Right. So because one molecule is converting into 2, so yes, the entropy is increasing. Okay. How this reaction proceeds, you see, did you write all these? Yeah. Just a second. Okay, you see the mechanism here. This reaction actually involves 6-member transition state ring, cyclic ring, which has 6 member. So you see this one, CH3 C double bond O, CH2 CH2H. This lone pair, it takes this hydrogen atom, and hence we get 6-member ring. 1, 2, 3, 4, 5, 6. So this involves 6-member cyclic transition state. Okay, so what happens? This comes over here. This sigma bond converts into pi, and this oxygen takes this pi sigma bond and goes out. So here we get CH3 C double bond O H positive, and we have here O negative, right, which further converts into this, comes over here resonating structure, and we get CH3COH double bond O, plus we also get this alkene, which is CH2 double bond CH2. That is how the product we get. One more important thing, if you have unsymmetrical structure here, then we consider the beta carbon or this lone pair will attack onto that carbon which is less crowding. Okay, so write down in EI reaction, beta carbon is the carbon beta carbon is the carbon which has less crowding. Okay, for example, if you have this molecule CH3 C double bond O OCH, here we have CH3 CH2 CH3, and when you heat this, then what happens? You see here, this is alpha and this is beta carbon, this is also beta carbon. Okay, this beta carbon is less crowded. We have 3 hydrogen, but here we have 1 methyl group and 2 hydrogen. Hence this lone pair will take this hydrogen, right, and we get a double bond here. So what is the structure we get? Well, the product we get is an acid plus an alkene, which is CH2 double bond, CH single bond, CH2, CH3. Understood?
Yes, sir.
What is the product we get here in this reaction? Diester it is, 2 ester group.
Student from benzene.
Benzene and 2 molecules of
acetic acid.
Acetic acid. Okay, so we have 2 beta carbon, one is this, another one is this. So this takes beta carbon from this takes beta carbon from this takes hydrogen from this, and we end up getting a ring, benzene ring, plus 2 molecule of CH3 COOH. Correct? Now, The second type of reaction we have is pyrolysis of xanthates.
So could you go back to the previous slide?
Just a second. Pyrolysis of xanthates.
Yes, sir, done.
Okay. One more point I would like to mention here. EI reactions are syn elimination reaction. Right? Write down. EI reactions are syn elimination reactions. Means this group OC double bond O R group at alpha carbon. This is important.
Could you repeat?
EI reactions are syn elimination reaction. Means this group at alpha carbon and hydrogen at beta carbon must be on the same side, right? Must be on the same side. So if you have the three-dimensional structure, then we always have these two on the same side for EI reaction, right? Intramolecular reaction. Okay. Xanthates, the reaction of xanthates is exactly similar to the reaction of ester. Okay. The only difference is here that instead of oxygen we have sulfur present. Okay. I'll just give you one simple example, right? We won't discuss this much. Instead of oxygen, if you place sulfur here, this CH2 CH3, when you heat this, you'll get the same structure, ethene plus so instead of oxygen, we have sulfur. That is xanthates. That is it. Nothing much we have in this one. Okay. Next reaction you write down. Pyrolysis of nitroalkanes. See this example. Nitroalkane is this CH3CH2 NO2. Pyrolysis means when we heat this, the mechanism is EI and the product is CH2 double bond CH2 plus we get this acid. This reaction is again syn elimination reaction. Syn elimination reaction. How it happens? This hydrogen, it attracts onto this oxygen, and we get again a 6-membered ring, and then finally the ring breaks. I'll draw the structure here, you see. Just a second. Just a second. Don't draw this. We'll write it this way. O minus plus, and then we have double bond outside. Okay, the coordinate bond we can represent this way. You see 1, 2, 1, 2, then 3, 4, 5. 5-member ring we are getting. So when it comes over here, this sigma bond comes over here, and this goes out as NOH, and we get this. Okay, so we get an alkene plus NO2H. HNO2 will get here. This is pyrolysis of nitroalkanes, exactly same like we have xanthates or esters. Okay. Next, fourth type of reaction we have.
So
Fourth
1 minute,
reaction.
we'll go back to the previous. Done, sir. Thank you. Done, sir.
Yeah. Now the next one is Cope elimination reaction. Write down, we use peroxide for this reaction. We use peroxide for this reaction, which releases nascent oxygen, and hence the reaction proceeds. So these are the reactions of tertiary amine. Okay. For example, if you have this molecule, CH3CH2 N CH3 and CH3. Okay, tertiary amine. When this is allowed to react with or heat with any peroxide like H2O2, or we can also use MCPBA. Okay, MCPBA. What is MCPBA? MCPBA is metachloro perbenzoic acid. Meta position, we have one chlorine. Perbenzoic acid is this. This is the structure we have of MCPBA. You don't have to, write down this structure. In the exam also we'll get this only. MCPBA. Okay. The product we get here is the alkene with respect to the larger alkyl group. Okay, alkene with respect to the larger alkyl group. Okay, beta carbon involves in this reaction. So here we do not have beta carbon, and hence this carbon involves in the reaction. So the product here you get, I write down the product. It is again an alkene, CH2 double bond CH2 plus we'll get NCH3 CH3OH here and the lone pair. In this also we'll get 5-member cyclic transition state. Okay, 5-member cyclic transition states. So what happens, all these reagents that we are using here, the peroxide, this peroxide releases nascent oxygen and the reaction goes this way. H2O plus will get a nascent oxygen, and in this we have a vacant orbital, right? This is vacant orbital. Now this vacant orbital can easily accept the lone pair of nitrogen atoms. Okay. So, okay, so this we have nascent oxygen. Now what happens, this nascent oxygen has one vacant orbital, so it can accept the lone pair of this amines, okay? Now you see this reaction here. The amine we have, this donates its lone pair to the nascent oxygen and it forms the structure which is CH3CH2 and CH3CH3 lone pair, and this lone pair it is given to this nascent oxygen, and the structure we get here is CH2H, then we have CH2 N O minus plus CH3CH3. Now this O minus takes beta hydrogen. This comes over here and this goes over here. So we get CH2 double bond CH2 plus NOH CH3CH3. This is the product we get. So in all these reactions you see, we are getting alkenes as the major product. We are heating also. Elimination reaction we have, so we are heating this. Finish all of you?
So just 1 second.
Wouldn't there still be a plus charge on nitrogen?
Where? Here. Finally.
Okay, wait, your bond is broken. So.
No, here we do not have, because this
Yes,
positive charge will be neutralized by this sigma electron.
Yes, sir.
And anyways, nitrogen, whenever has 3 bonds, it has no charge on it. Done?
Yes, sir.
Okay. What is the product in this reaction?
Done, sir.
Done. So what is the product we get? In the first step, we'll get this. Yes. And then this is alpha, this is beta carbon. So If you follow the mechanism, we'll get the product as this. Is it correct?
Yes, sir.
Okay.
Yes, sir.
So all these elimination reaction you see, we are getting alkenes. In fact, elimination reactions mostly gives you alkene overall if you see. The last reaction we have discussed for elimination reaction. Now the last part of this chapter we are going to start, that is free radical intermediate and its reaction. Okay, few reactions we have already done in this hydrocarbon chapter. Just we go through once into this. Okay, so free radical, we have discussed the basic structure of this and properties. This is free radical, right? With one unpaired electron. Quickly tell me, what is the number of sigma bond? It has 3 sigma bond, 0 lone pair, no vacant orbital, one unpaired electron. It is neutral. There is no charge on this, so it is neutral. Unpaired electron, it is there. It means it is paramagnetic, right? 7 electrons in the outermost shell. Electron deficient, but cannot accept one pair of electron. sp2 hybridization, trigonal planar it is, and stability is what? Is directly proportional to EDG, electron donating group, and inversely proportional to electron withdrawing group. Any doubt in this? All these properties we have for free radical. Okay. Finished?
Yes.
Tell me.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now you see the free radical has, or free radical shows 2 types of reaction generally. Okay, 2 types of reaction it shows. The first one is, I'll write down here. It shows a reaction of 2 types. The first one is combination reaction.
So I have a doubt.
Yes.
So what's EDG and EWG?
ED is electron donating group. Or Rajdeep,
Okay.
right?
Yes, sir.
Yes. EDG is electron donating group. EWG is electron withdrawing group.
Okay, sir.
Okay. Combination reaction, and the second type of reaction we have, which we also call it as disproportionation reaction. What is the another name of disproportionation reaction? It is redox reaction also. The same molecule goes under oxidation or reduction. So what are the 2 types of reaction? We'll see. Did you finish this?
Yes, sir.
Okay. The first reaction you see, that is combination. combination reaction. So in this reaction, what happens? The activation energy is 0, right? 0 activation energy means the product and the reactant molecule have same energy. There's no difference into this, okay? And combination means, suppose we have one free radical like this and another free radical like this. These two simply combines and forms a molecule which is like this. This is combination reaction. Okay, this is one type of reaction. Another type, like I said, is disproportionation reaction. This disproportionation reaction is, we also call it as, it is a type of redox reaction where the same molecule get oxidized and reduced. Same molecule get oxidized and reduced. Okay, this type of reaction generally shows by tertiary radical. In general, it is observed in tertiary radical. Okay, now if I have a radical, say CH3 and CH3, this is the radical, and when it combines with the same radical this way, okay, we'll get a transition state here where this hydrogen is trying to attach with this carbon, and this bond is about to break as a homolytic cleavage takes place here. So transition state here is something like this: carbon CH3, 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 and this bond is about to form H. This bond is about to break, CH2, C, CH3, and CH3. Where we have the radical here, it is present. We have a radical here. Okay, and then finally what happens? This bond breaks, it comes over here, and this is taken up by this carbon, and we end up getting two products here. One is an alkane, which is CH, CH3, CH3, and CH3. This product we get. And the another one is this unpaired electron. This unpaired electron combines, and we get an alkene, which is this. Okay, this you see, it gains hydrogen, so it goes under a reduction. It loses hydrogen, so it goes under oxidation. This is oxidative product, right? So same molecule is going under oxidation and reduction. Hence the reaction is disproportionation reaction, right? In any reaction, both combination and disproportionation competes with each other. In any reaction of free radical, both reaction competes. Like we have SN1 and SN2 competes with each other. These two also competes. Okay, so activation energy for this reaction is not equal to 0. Okay, it is a slower reaction, means slower than the first type combination. Okay, and both reaction compete with each other. Write down these points.
So, but in first one, if EA is 0, shouldn't that be the most like favored reaction?
change in EA is 0. There is no change in activation energy. Okay, so overall the change would be like this, that whatever the energy we have here, the same energy of the product we get here. It means this kind of reaction is neither exothermic nor endothermic, we can say. All three types possible, no? Delta H greater than 0, less than 0, equal to 0. So these are equal to type reactions. Yes, mostly these kind of reactions are rarely we observe. This kind of reactions is more favorable here. But it depends also upon the groups which are attached to the free radical carbon, right? If suppose if crowding is more, right? If crowding is more, then suppose if this group is very large, this group is very large, this group is very large, okay? Then when these two radicals come close to each other, then these groups produces repulsion there,
Yeah.
right? So when the crowding is there around the free radical carbon atom, then the tendency to go under combination reaction decreases. And that's why I have written here 3-degree radical is more favorable. So we cannot say which one is more favored or not. It depends upon this condition also. What groups are attached on the 3-degree radical. Okay.
So if all of them are methyl groups, we can't say which one will favor.
Sorry?
So if all of them are just methyl groups.
No, if tertiary is there, then it goes under disproportionation reaction mostly.
Okay, so in this case,
so I'll write down here. This is, you see, I'll write down here. If you have 1-degree radical, so for 1-degree radical, we'll go with combination. With 3-degree radical, we'll go with disproportionation, right? With 2-degree radical, both possible we have, combination plus disproportionation. That's why we'll write down here all possible product. Remember, Wurtz reaction, we get all possible product there. Alkene, alkane, everything. Understood?
Yes, sir.
Just a second. You know, I've started nomenclature to these 11th grade kids, you know, this year actually. Okay, so they are very energetic right now because they know the basics of nomenclature. 10th grade they have already done. Okay, so whatever assignment I send them, they send me the answers, quickly. So what is wrong in this? I did not get this answer.
So that excitement will be there for like 2 days. When they get to know how it is, then they'll...
Sorry, what?
When they get to know how it really is, then they'll understand.
Yeah, that's how. So they are getting it nowadays because basics they have already. So they are solving questions and sending me doubts and all. That's how. Anyways, so this is 2-degree radical.
Can we do their chem-ons for fun?
What?
Like the 11th graders, can we do their chem-on tests for fun?
Chem-on test?
Yeah, like as practice.
I have taken one test last Sunday, like not chem-on, but normally only chemistry it was. So they have done pretty well. Out of 130, they scored 120, 115, like that. So it's the basic questions of nomenclature. So that's why they are enjoying a lot nowadays. But the time is going to be worse for them. That I am very sure of.
So can we do their tests?
The nomenclature test, you want?
No, like in general, when they have their CAMON test, can we also get the link for that?
If you want, you can write. That's not an issue. It's there. If you want, you can write. We'll like, you know, if you want to write, just let me know. I'll just talk internally and let you know that how to access those tests.
If you do, you expose yourself to the greatest dab of them all.
What?
So the
Scores
issue
you're
is
talking about.
if you take it and if you don't top, then that's a bit of an issue.
Okay, you are thinking about like if they got more marks than you, right?
They probably will. I mean,
yes, it's possible. It's possible. They are just 1 year junior to you, so it's possible.
It depends on their level of like.
Yes, correct.
Their
correct.
level
But it's
basically.
possible. Like in every year, there are 2, 3, 4 kids who are very sharp actually. So it's possible. That's not a big deal. But anyway, so let it be. So the crowding, if increases, so the reaction goes under disproportionation. If it is 1 degree, then combination. Okay. One more thing here, which has been observed, right? It is experimental fact we have that if you increase the temperature, right, as temperature increases, percentage of disproportionation reaction increases, and that the percentage of combination reaction decreases. Means basically at higher temperature, disproportionation favors than combination.
So is this because combination like results in a decrease in entropy?
Decrease in energy we cannot say. In combination there is
entropy,
no.
Sir.
We can relate that with entropy. Yes, entropy decreases. Hence, at higher temperature, disproportionation favors. You see, disproportionation may we are getting 2 molecules, right? One is alkene, other one is alkyne, right? So, however, the number of molecules are same in disproportionation, 2 on the reactant side, 2 on the product side. Okay, so exact idea of delta S, whether it is greater than 0 or less than 0, is is difficult to say over there. That's why I said it is experimentally determined that temperature increases, disproportionation reaction increases, and combination decreases. Okay, but little bit of idea you can correlate from that entropy thing. Okay, next point to write down: if the molecule has 2 free radical, if the molecule has 2 free radical, they combines to form either a pi bond or a ring. They combines to form either a pi bond or a ring. Okay, for example, if you have this radical CH2 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 radical, so these two combines and forms cyclopropane. Just a second. Cyclopropane. If you have this radical on the ring, if you have 2 radical presence like this, then this combines and forms a pi bond.
So is that a minus sign on the other side?
No, it's not a minus. Ignore this. Okay, these reactions are, you see, within the molecule the reaction is taking place. So these reactions are intramolecular reaction. Okay, intramolecular reaction. And intramolecular reactions are irreversible in nature. Irreversible. And hence, irreversible reaction, we know it is rate controlled, So we just see the rate, how fast the kinetic product it is, right? So how fast the product forms. Okay, rate control. So it is how fast the product forms. It has nothing to do with the stability of the product.
So for free radicals, you can apply this thing, rearrangement.
Free radicals rearrangement possible.
Okay.
Stability of product. See why I have discussed these 3 points, which is written in yellow. Because you see, in this reaction, you can ask me, sir, 3-membered ring is highly unstable because of high angle strain. Right? Then why it is forming? That's the question you can ask, no? So why it is forming, the reason is this. It is intramolecular reaction, and intramolecular reactions are irreversible reactions. Irreversible reactions are rate controlled. Like we have discussed KCP and TCP. KCP is what? Kinetically controlled product. So we'll talk about the fast forming product. Okay, the product which forms with a faster rate, not the stable product. TCP is thermodynamically controlled product. We'll talk about the stability of the product, and hence we discuss what? The more stable alkene we have to form. So we are not discussing this, the stability of this molecule. It is irreversible, so how fast it forms, that is what we mean. Okay, even if you see this example, if you have radical like this, and we have one more radical like this, what is the product we get? Yes?
Butane.
Cyclobutane.
Hexane.
Cyclohexane.
Cyclohexane, right?
No, it is radical here, 3 and 3, or cyclohexane. Cyclohexane we get here.
Hexane, right?
But whatever you write, whatever you write, it does not matter because this reaction is not possible. You do like this only. You know why? Because this reaction is intermolecular reaction, but this favors intramolecular, right? Intermolecular reaction is not possible. Combination reaction, right? 1 degree radical, 2 1 degree radical combines and gives combination reaction. This is intramolecular reaction, this one is intermolecular, so this is not possible. Means the basic thing is what? Before combining these two radical, these two itself combines and forms 2 cyclopropane. That is how. It's a fast forming product. These two combines together form cyclopropane. Okay, now a few reactions we'll see into this one, the basic theory we have discussed. Could you tell me the product here? CH3, CH2, CH2 radical. And we are taking 2 molecules of this.
Hexane.
All these we have excess of it.
So excess or just 2 molecules?
What?
So is it 2 molecules of each of them?
Yes, yes, yes. Okay. You have 2 molecules of all these.
So in the second one, you get like 2 products.
Yes. Second one is 2 degree radical. So it gives combination as well as disproportionation. One disproportionation reaction, I have shown you the example. Try that and write it down, the product. Done? Okay. So in the first one, the product is hexane, 1 degree. So it goes under combination reaction, hexane. 2 degree, it goes under combination plus disproportionation. So under combination reaction, you'll get this 2 cyclohexane ring attached like this, and the disproportionation product is cyclohexane plus cyclohexene. Is it right?
Yes.
These two are disproportionation, these are combination product. So here we have only
combination. Only combination.
Combination, right? So this is the product we get.
But we can't have rearrangement in this one, sir.
No, it's like we are just talking about what is the possible product. We are not doing rearrangement and all. That is, we are not considering it. Just we are looking at what happens with the radical if you have. So this also gives you what?
Combination.
Combination, and this is disproportionation. No,
combination.
Disproportionation. Okay, major product is this.
So the double
here what
bond,
we get?
So the double bond can be
double
any
bond.
one of.
Yeah.
Any side you write same thing.
Okay.
Okay.
So in the first one, where do the 2 extra hydrogens go, sir?
Here.
So yes, it will be CH3, CH2, CH2, but hexane will have only 12 hydrogens, right?
What? We have 14 hydrogen, no?
Yes, sir.
3, 5, 7 to 14. Correct?
Oh, sorry, sir. Hexane. I thought you said cyclohexane. Sorry, sir. Sorry, sir.
Okay. This reaction, you see, we have benzene and 2 unpaired electrons, free radical like this. Okay. This always goes under disproportionation reaction. Sorry, this thing, combination reaction. It combines with the another molecule this way. Radical has 1 electron here, 1 electron here, plus the another such molecules. It combines with this and forms the product as this. So we always have combination reaction here, not disproportionation. Combination reaction, not disproportionation. This is the product we get here. Why? Because triple bond is not possible in a ring, 6-member ring. For triple bond in a ring, the ring must have at least 8 members. Then only it is stable. Okay, write down. For a triple bond, to form a triple bond in a ring, the ring must have at least 8 members.
So what is this compound called? The one which is found?
What?
So what is the name of this compound which is found?
This one, biphenyl we can say. Biphenyl, biphenyl we can say.
Okay.
Okay, so the ring must be 8 membered. That's why this does not go under intramolecular. What I'm talking about does not go under intramolecular combination reaction, right? These two are not going into combination. Now, if you have compounds like these, there are a few examples that you must understand. Like this compound, you see, we have a double bond here and free radical on this. Okay, so here also we do not say that this will go under intramolecular combination reaction, because this becomes then
become anti-aromatic.
Anti-aromatic. So what happens? This combines with the another such molecule, and it gives the product, which is this. This is the product we get here. Got it?
No, but why will it combine? It's already aromatic in the first place. Right?
It's free radical, right?
It's aromatic, fine, but radical is very reactive, no? So if it combines, possible product is this, this won't form.
Okay.
We have this also. It's not like aromatic compound does not go under reaction. Benzene goes under reaction, no?
Yes, sir.
One more example you see.
Previous. Yes, sir, done.
Okay. Now this one is also important. If you have a molecules like this, carbon here, phenyl, pH and pH, and this carbon has one radical on it, right? In this reaction, what happens?
So disproportion.
Tell me.
I think disproportionation.
Disproportionation. For disproportionation, what is required?
So 3-degree carbon.
And you look at that reaction that I've done, disproportionation. You see that?
So we need a hydrogen there.
Hydrogen, where?
It's not here, so we can't use.
Do we have hydrogen present?
At beta position. Right?
So do we have beta hydrogen here?
No.
Okay.
We have no beta hydrogen, right? Now you see this example, if you haven't done it before, in the exam you won't get it for sure. Okay, so no beta hydrogen, disproportionation is not possible. Do we have combination possible?
No, sir. Bulky groups.
Bulky group is there, so combination is also not possible. So do we have reaction possible here? Disproportionation is not possible, combination is not possible. Then also this gives a product which is something like this. It is not like, it does not give any product into this, but this also combines in this way. pH, pH, this combines with the ring. Gives something like this. Because what happens, you see, this goes under resonance, right? And resonating structure of this, if you draw, it will be something like this. This comes over here, half arrow, this comes over here, and this comes over here. This forms a pi bond here, and we get a radical, which is something like this. Did you get it? You get a radical here. Now this end and this carbon combines, gives you this compound.
So that carbon is making 5 bonds.
Where?
So the second phenyl ring.
Acha, here. It's, oh, I've drawn it wrong. This is okay. It should be this. So it should be like this.
So this is also 2 molecules of these, right?
What? Yes, 2 molecules. That is understood here.
So, but
2 molecules.
here why won't there be hindrance?
Huh?
Why won't there be hindrance in this?
Because you see, this is the molecule we have phenyl like this, no? This is a phenyl we have. Okay, ring we have, but this side we have only hydrogen here. If you place any NO2 group this side and this side, then hindrance will be there. In this case, the hindrance is not that strong, so that it hinders the bonding between the 2 carbon atoms. If you have any group attached at this point and this point, then hindrance will be there. It's relative, okay? In this way, if you try to combine this carbon atom, then these 2 phenyl will repel each other, right? So this bonding is difficult, but this is possible to some extent. Right? That's why I said, if this kind of examples you haven't done, in the exam you won't get it. Clear?
Yes, sir.
Okay. Now, these are the few reactions of free radical we have discussed. Just a second. Okay, I saw your query now here. What was your query here? You are talking about KCP. That's what we did, no? Kinetically controlled product, irreversible reaction. Oh yeah, I saw this. Sorry. Anyways, so you know, what are the conditions we have under which free radical may form in any reaction? Okay, so that we'll see first, and then we'll see the reactions of free radical. So formation of free radical. Free radical. The first thing is, if you have a peroxide, ROOR, and you heat this, then what happens? Homolysis of this bond, and it gives you 2 molecules of RO radical. Okay, like it is 2 lone pair we have on this oxygen atom and 1 unpaired electron like this. So this is possible. When you heat a peroxide, you'll get this. Another possibility is what? Halogen atom, halogen molecule. It also has lone pair on it, and because of lone pair repulsion, the bond is not that strong. So when you heat this, or in presence of sunlight, HNu, or you write heat, or if you write high temperature, that is also fine. High temperature. Okay, this bond goes under homolysis, and it gives 2 radical of this. This is another possibility. Third one, if you have a bond like this, oxygen and halogen atom bond like this. Here also slightly you heat this, dissociation takes place, homolysis, and it forms 2 radical like this. It is all because of lone pair repulsion. The bond strength is weak, and hence it can go under homolysis. Similarly, if you have this, an alkyl halide Rx, suppose RCl I am taking, and in presence of metal. So we know metal provides free electrons, that Rx bond becomes weak. Okay, homolysis takes place, becomes R radical, and plus Cl minus it forms. Okay, this is the Wurtz reaction. What?
So why Cl minus?
Because one electron is from here, one electron from metal, forms Cl minus, which further combines with Na plus, forms NaCl.
Yes.
Okay. This you can understand this way also. In some book, they have given this mechanism. Na metal loses electron, forms Na plus and E minus. Now RCl, in presence of this free electron, this electron attacks onto this alkyl group, and this bond pair is taken up by this chlorine. So R, one single electron, and Cl minus. Like this also they have explained in some book. Okay.
Yes.
Finished? Okay. Now when you have carboxylate ion Rc double bond O, O minus, this goes under oxidation, anodic oxidation, and it forms Rc double bond O, O radical plus one electron goes out. Okay. Now this radical also has tendency to eliminate neutral molecule to give new radical. This is the property
CO2.
of free radical. This comes over here, this comes over here, these two radical combines and it forms R radical plus CO2. So this is the property of free radical, that it combines, that it eliminates neutral molecule to form a new radical. This is the property. Another example is where the free radical forms when we have diazo compound and double bond N bond is present. So when you heat this, this bond breaks and it forms two phenyl radical and N2 gas evolves in this process.
Which bond breaks over here?
Just a second, guys. Let me go back first. Yes, copy it down, Varun. You copy this, I'm coming in a second. Yeah. So these are the conditions under which the free radical formation of free radical is possible. Okay.
So over here, how exactly does the bond break? Does like one of the double bonds break and give it to the
This one?
phenyl? Yeah.
It's a simple one. You see, when you heat this, then this one electron comes over here, one electron comes over here, and same thing happens here. These bonds form a triple bond here.
Oh, okay. Understood.
Now the next thing is the reaction of free radical. This is the last part of this chapter. Okay, reactions of free radical. Some of the reactions we have already done, right? Like the first reaction, very common one, important also, is Wurtz reaction. Okay, Wurtz reaction is what we have Rx, 2 molecules of this with Na, dry ether, it forms Rr plus NaX. Okay, so this is used for what? For symmetrical alkanes. Okay, we have 2 types of mechanism here for Wurtz reaction. 2 mechanism possible. The first one is we have discussed already, and that is free radical mechanism. Do I need to discuss this again? Yes?
So,
Tell me first.
so we know it.
Right, okay, so few points, just write it down. We only get symmetrical alkane with even number of carbon atom. We only get even number of, sorry, symmetrical alkane with even number of carbon atom. Next point, the alkyl group. The alkyl group should be 1 degree. The alkyl group should be 1 degree. If not, then disproportionation reaction is also possible. If not, then disproportionation reaction is also possible. And we get a mixture of alkane and alkene.
So what was the other mechanism?
Ionic mechanism. We'll discuss that. First, we'll finish this. We'll discuss that. 2 mechanism. We have free radical and have you heard about ionic mechanism of Wurtz reaction? No. Okay, so this point is important. Alkyl group should be 1 degree. If not, then disproportionation reactions also takes place. And we get a mixture of alkane and alkene. Dry ether, why we use? So that Na does not react with water. If you do not take dry ether, Na also reacts with water. Okay, so to eliminate that, one second, guys. I did not take the attendance screenshot. No, let me just take it. Got it. Rohit. Okay, done. Right, so this is important. So that's why we are using dry ether, so that Na does not react with water. Now you see, sometimes they ask this question in Wurtz reaction. We have this CS3, okay, 2 molecules of this. Na, dry ether. What is the number of product we get in this reaction? That's what I am asking Ruchir Parekh. Is it 1, 2, 3, 4? How many products possible?
So do we have only
Oh, Vikas
two
is
of
getting
these?
3.
So it's
Yes.
Only 2 of these.
Sorry, I didn't get you. Come again.
So do we have only 2 of the reactant?
2 of the reactant. Yes.
Sir, I'm getting 3.
Vikas is getting 3. Oh, Abhiram.
So
Abhiram, you're
I'm
getting
3, but that's assuming that we have enough of them to
Yes,
do both
that's why I
reactions.
was asking.
Yeah.
See, actually, it's very simple. We have already done combination disproportionation. So it is 2-degree halide, no? So it forms what? It forms the radical, which is this CS3CH CS3 radical. Okay. Now with this, what possibility we have? One possibility is the combination reaction, which is this. And hence the product is what? The product is this CH CS3 CS3 and CS3. This is one of the product possible. Another product is
Propane.
Propane and propene.
Propane.
And disproportionation reaction gives you CS3 CH2 CS3 plus CS3 CH double bond CH2. So 1, 2, and 3 product we get into this. And in JEE, if they ask the question, they'll ask you these kind of questions only. They won't ask you, okay, Rx plus Na gives you what? They won't ask you this. Okay, so this product is by disproportionation. This is by combinations. So whenever you have 2-degree halide, okay, alkyl halide, goes under Wurtz reaction, we consider all the possible reactions. Okay, did you get it, all of you?
So but won't we need 4 of CH3 to form this?
What?
So won't we need 4 of the reactants to be able to form these many carbon atoms?
No. See, actually what happens, this 2 we have, and this we have number of moles, right? 2 moles of this. So there are many such molecules.
Okay, so I understand.
Right. So 2 moles means 2 moles. There are so many molecules present. Okay, that's why we write all possible products. Clear?
So will it be equimolar over here? Like, will you have
symmetrical alkanes are preferred? So if they first of all, they won't ask you which one is major or minor. But if they ask you, then this is the major product we'll go with.
Okay.
Okay. Fine. So this particular mechanism, free radical mechanism, we have already done. But the second type of mechanism that we have, we call it as ionic mechanism. And this we haven't done. Why we haven't done in the hydrocarbon chapter, you will get it now. Okay, and that's why I feel this particular reaction mechanism, we should do this after nomenclature, right? After nomenclature, we should do GOC, then we can do isomerism, and then we should do this reaction mechanism, and then hydrocarbon. So you'll understand this, why we haven't done this particular mechanism that time. See, ionic mechanism is, we have Na, right? So 2 moles of this will take, it gives 2 Na plus 2 electron. Ions are involved into this, that's why it's ionic mechanism. In the second step, Rx, this electron, free electron, it forms R radical plus X minus. This we already know why it is happening, because this comes over here and this bond pair is taken up by this X, it forms this. Okay, now this this radical takes one of the electron which is here left, because we have already used one. So one is left, so one electron is taken up by this and it forms R minus. So this is a carbon ion. So intermediate is a carbon ion here, right? Now this carbon ion in the third step, R minus, this attack onto the alkyl group, alkyl halide, because it is partial positive charge, it is partial negative charge. This comes over here, Cl minus goes out and it forms Rr plus X minus. This 2Na plus this X minus forms NX. Did you get it?
Yes, sir.
Right. Now,
Yes.
two things are very important. You see, first of all, the intermediate is a carbon ion, right? This alkyl group that we take, this must be 1 degree for this. They can ask you a question on this. 1 degree must be 1 degree alkyl group, because if it is not 1 degree, then there are chances of elimination reaction. If not, then goes under, write on it properly, goes under elimination reaction, and the product is what in that case? Product will be an alkene. Whatever, depends upon alkyl group, but yes, alkene we get. Okay, that's why this should be 1 degree, this thing, 1 degree alkyl group. Now this attack here, this attack is SN2. This SN2. So inversion is also possible. If it is tertiary group, then inversion will be there. Okay, so all these things, SN1, SN2, we did not know that time. Okay, when we were doing hydrocarbon last year, class 11. Okay, so that's why this mechanism I did not discuss that point of time, ionic mechanism. Now you understood this? Easy?
Yes, yes,
right? So always keep that in mind. They can ask you, under Woods reaction, you have to form this product. What should be the alkyl halide group you should take? They won't ask you simple thing, this plus this under Woods reaction, what is the product you get? They won't ask you this, okay? What is the substrate you should take for this particular product? Okay, information that I have given you here must be 1 degree. If not 1 degree, then what happens? Based on this, they can ask you some question. They can also ask you how many products possible that we have discussed. If you have 2 degree alkyl halide, it goes under, disproportionation plus combination. So alkenes, you get over there, right? So all those things, these things, the last 3-4 points that we have discussed, apart from the product, how do we get a product in a reaction? Apart from that, all these things are very important as far as JE is concerned, right? JE exam is concerned. So this is the first reaction of alkyl, free radical mechanism, free radical intermediate, not mechanism, free radical intermediate, okay? So there are a few more things here, some examples we have, and then the another reaction is cold electrolysis, okay, of free radical mechanism. We'll discuss this next class. There are a few things left, not much. So I think I'll take more like probably like 1 or 2 hours next class and we'll finish this. Okay, 1 or 2 hours maximum we'll take and we'll finish this. So what is the next chapter we have to start with?
So since like we've done haloalkanes mostly, we could do coordination compounds if you want.
Coordination, see, actually I haven't done coordination anywhere. In some classes I have done electrochemistry, right? So for a change, if you want, we can start with electrochemistry or haloalkane, haloarenes. There are few things left. Most of the reactions we have already done in this. So those things which are left, we can do that also. But I would suggest for a change, we are doing organic for so many days, but I would suggest that we should go for electrochemistry now.
Yes, sir.
Yes, sir.
Fine.
Yes.
Okay, so, and if you are comfortable with it, just let me know. I am not going to follow the school curriculum, whatever they are doing in the school and what stuff they are taking in the school. I just want you to prepare for competitive exams. So I'll just do like that only. Okay. The way I have done last year in Rajinagar. Okay, I have gone like this only. Yeah.
So on the group, you had asked if you want some advanced stuff for equilibrium. Could you send that?
Right. You want that?
Yes, sir.
Yes.
Okay, I'll share. Who all want?
So which
You can just send it on the.
I'll send this on the group.
Yes,
Okay, if you want, you can solve this. It is chemical equilibrium only. Okay, you can solution plus answer key, all things are given there. So you can solve those questions. Okay, this for advanced, mains, upper, we have a one level upper than mains, and then till advanced level it goes. Okay, few questions you will feel it is easy, and then till advanced level questions are there. Okay, so I'll share those PDF on the group. Correct?
Yes.
So yeah, so fine guys. So what we'll do next class, we'll continue with this. We'll take some time to finish this off, and then we'll start electrochemistry. Okay.
So is this chapter there for KMON? This coming
KMON, you won't have much questions. One or two questions may be there from organic chemistry where reactions were there, right?
So this chapter is not there, right? That much.
See, like again, I cannot tell you because this chapter you must have seen. We have gone through the entire organic chemistry, ester, carbonyl compound, amines, many reactions we have seen, right?
Yes,
so
sir.
This chapter is not there in the syllabus, but yes, you can get one or two questions of organic chemistry, which we have done in this chapter. Some references are there, okay? But you don't have to do this chapter particularly for the KMON test. That is the one suggestion I'll give. But little bit of understanding of organic chemistry, you'll see there's one or two questions that you must get from this.
Yes, sir.
Okay?
Okay, sir.
Fine. So we'll wind up the session, guys. And one more thing, I'll share some more assignment on this. One assignment I have already shared on reaction mechanism. I hope probably you have done that. Okay.
Yes.
Some more assignment, DPPs I'll share on reaction mechanism. You must solve this. Okay. Without solving, you won't get it. Okay. Thank you, guys. Thank you so much.
Thank you,
Bye.
sir.
Yes, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.